Hello, welcome to a video on section 4.1, which is about extreme values of functions. So here we're going to talk about absolute global extreme values. An absolute maximum is considered the highest y value in the specified domain. So for example, if I were to draw a curve like this, we can say that that point right there would be an absolute maximum because that would be the highest y value for all real numbers here. An absolute minimum is when you have the lowest y value in the specified domain. So if I drew a different type of parabola, one that opened up, the vertex right there would represent absolute minimum because that's the lowest y value if my domain was specified to be all real numbers, or actually for any domain. Or actually, I take it back, because if I could state a domain where the vertex was not included. So more formally, if f is a function of domain of D, then f of a is absolute maximum on your domain if and only if your y value, f of a being the absolute maximum, is higher than any other y value in your specified domain. Likewise, you have an absolute minimum on your domain if and only if, and that should be f of b, by the way, that's a typo right there, if that y value is lower than any other y value for all x in your domain. So let's consider the graphs down below. So each of these represent y equals x squared, and they all have different domains. Like, for example, the first graph has a domain of all real numbers, so it would look like this. This would have 0 to 2 with endpoints at 0 and 2. This would have an open circle at 0, and of course, it's an endpoint at 2. And you have open between 0 and 2 there for that graph. So if we look at the first one, there would not be an absolute max because we don't know what the highest point of that graph would be. Basically, both arrows point up. You know, when x is going towards infinity, y is going towards infinity. Likewise, when x is going towards infinity, y is also going towards infinity. So we can't say it's an absolute max for the first graph, but there's definitely an absolute min. And the absolute min is 0. We typically state the y values for absolute min or max. Now what about for the next one? Here we have a closed interval between 0 and 2. So the highest y value in our domain clearly is 4, and our lowest y value is 0. But if you have an open circle, as we see with a 0, so it's an open interval, still have an absolute max of 4, but we don't know what the absolute min is because we get really close to 0. For y, but not exactly 0. And in here, for the last one, so 0 and 2 are not included, so you don't have absolute max or min for either one. So what needs to be true about the interval to guarantee that both an absolute max and absolute min will exist? Well, the only time we had both an absolute max and min were right here. And notice that was a closed interval. So we need a closed interval for both absolute min and max to occur. What else needs to be true? Well, let's look at the function below. And actually, this one's defined from 0 to 5, not 0 to 6. Is there an absolute max value? Well, we definitely see that we get pretty high around this area compared to this portion of the graph and, of course, the rest of this graph. But because that there's no point included at x equals 2 comma 4, like we get really close to 4, but not totally right on 4, we have a problem. And so we notice that if we don't have continuity, there's a good chance that you may not have an absolute maximum value. So there is no absolute maximum value here. And again, we have a discontinuity. Now, what if I redrew the graph to make it look like this? Now, in this case, I do have an absolute max right here, and an absolute min right there, my interval from 0 to 5. But it doesn't necessarily guarantee that I will, and that's the thing. We're talking about guaranteeing. It doesn't necessarily guarantee that I'm going to get an absolute max if I'm not continuous. So definitely we want continuity. Because if you have continuity, you're guaranteed to get an absolute max and min. Continuous, or let me rephrase that. Function must be continuous on its domain. So this actually leads us to the extreme value theorem, which we pretty much have explained it without realizing it. I've now explained the theorem to you. If f is continuous on its domain on a closed interval, then definitely your function will have an absolute maximum and a minimum on the interval. And usually if we don't, if we omit the word absolute, okay, I'm not sure what's going on here. It's kind of bugging out. If we omit the word absolute, it will be implied that that's what we're talking about. Okay, so let's move on to the second page. So we can use the word extreme value as a blanket description for maximum values. In addition to absolute, we also can use the word local and relative. So local means anything that's nearby, right? So local max is y values higher than other y values nearby. The local min would be the same thing. So let's look at this graph here. We have 5 points A, C, E, D, B. And we see that at A, we definitely have an absolute min. At D, we have an absolute max. And we see that we have local max and mins at those two places. And then here, this would be a local min. So you see how for a time being, it seems like that's kind of like the highest point. For a time being, that seems like the lowest point. For a time being, that seems like the lowest point right there. But that's being the highest point, that being the lowest point. So more formally, we could say the following, that f of c in this case is a local maximum because our y values were definitely less than or equal to f of c for some open interval containing c. So what if my open interval was from there to there? So I don't have the endpoints, but definitely at point C I had a maximum. And for some interval, it could change, of course, if my interval went from this point to that point. Then, of course, I wouldn't have a local max. So you do have to be careful with how the interval is defined. You have a local min at point, actually in this case it was at point E. Just being consistent with what we see in the graph here. For the same reason. If you chose some interval where E was included in that interval, then your y value at point E would be the lowest point in that interval. Let's talk about half-open intervals, though, for local maximum values at the endpoints of the domain. So here we have example 3, ratifying extreme values where they occur. So here we have an absolute max, absolute min. Well, I don't have it for sure, but I'm just going to write this down for now. Local max, local min. And here we have absolute max, absolute min, local max, local min. So let's start with part A. Do we see any local absolute maxes here? The answer is no, because that point's not included at 4, 3. So we don't quite know what the highest point is. And likewise for absolute min, we see a circle there as well. So there's no point included for 0, -3. So also we're not quite sure how low we can get. We can get close to -3, but we don't know exactly. So definitely it's no and no for the absolute max and min. But let's talk about local max and local min for part A. So interestingly, we see that there's a dot right here and a dot right there. Now if I contain an open interval, say like that, and that could be from like say -1 to say 1 for x, we see that that dot right here is definitely going to be the highest point. So we would say that we have a local max of -2 at x equals 0. And let's say had another interval, and say in this point, say I did it's kind of hard to show. Maybe if I could, no, I'll just do this. No, this is still getting tricky. Okay, let me see if I can get the highlighter. So we see that this dot, well, this dot could represent a local min of 2 at x equals 4. Because if I define my interval in such a way where it's half open, so I definitely have it open here, and maybe I could like close it at like 3.5, we see that at x equals 4, that would be a min. So definitely that would be something that would occur there. For part B, definitely have absolute max at 2. That's the highest that y ever gets. And this is for x in the following interval, from -2 to 1. So definitely we have y equals 2 at a lot of different places between -2 and 1 inclusive. Absolute min, there is none, because you have these endpoints are not included. We would have a local max at a value of 1 at x equals -4. Again, we're looking at -4. You could create an interval where from -4 to -3, definitely the max would be that point, which has a y value of 1. Looks like we don't have a local min here, so I'd say no. Okay. So looking back at the graph for example 2, so here's a graph for example 2, which is right here. We found that we had local extreme values when there was an endpoint, and also when the derivative had equaled 0, or if our derivative was undefined. So as a definition, this is a very, very important thing to know. I'm putting a star next to this and also the one right below. A critical point of a function f is a point in the interior of its domain at which f prime equals 0, or if f prime does not exist. See, let's go back up here again. So notice how the derivative here was 0, and the derivative here was 0. Also notice how the derivative here is undefined because it looks like we got a corner there where the left-hand derivative does not equal the right-hand derivative. So whenever our derivative is 0 or does not exist, we would say that we have a critical point there. And extreme values occur either at endpoints or at critical points, like absolute min or absolute max. So that's very important. Just as some of the things I just remembered is that you definitely want to make sure you know this really well too. And definitely want to make sure you know this. So anything in the boxes, make sure you got that down. And likewise over here. So anything with stars, must know. Very important. Okay. So let's talk about local extreme values, or local extreme values theorem. Now, if your function has local max or local min at some point C, and the derivative does exist at that point, we can say that the value of the derivative at that point does equal 0. Now, just so you know, the converse is not necessarily true. Like you could say, oh, what if my derivative is 0? Then I know I have local max or min. Well, let's look at this case here. See how my derivative here is 0? And actually it's at 2. X equals 2. You have a horizontal tangent there, but we don't have any max or min, so we can't reverse this statement and make it true. The contrapositive is true. I remember the contrapositive. That would say that if you don't have a derivative that equals 0, then you don't have a local max or local min. That's something we could say with confidence. Here, f prime 2 equals 0. Now this definitely is a local max. Actually, it's also an absolute max, but we can call it local max. Sometimes those terms could be interchangeable. If your local max happens to be an absolute. Yeah, we have a local max, derivative there is 0. Now here we have something that's undefined because that's a vertical tangent line. So f prime x does not exist. But notice that we don't have any extreme values. But here we do. And that's an absolute max. And f prime 2, again, does not exist. So we could also extend this to when the derivative does not exist. If you have an absolute max, there's a good chance that also the derivative could be undefined. But that's not always true if your derivative is undefined, because here the derivative is undefined and we didn't have a max or min. But what we do want us to look out for, if our derivative equals 0 or undefined, that's typically where we'll see our extreme values. If they're not there, then they'll be at our endpoints. So very important, that's where we look. The critical points, which is when your derivative equals 0 or does not exist, or the endpoints. So let's apply this to example 4. So what I'm going to do is I'm going to take the derivative. But before I do that, let me prep this function so it's easy to take the derivative. And we just had our derivatives test, so hopefully you guys are comfortable with what I'm doing. So there, just the power rule. And here the formula for derivative ln is just 1 over whatever's inside the parentheses, but I got to do the chain rule, so times 2x. So my derivative is negative 4 over x squared plus 2 over x. Now, very important that we're going to want to combine this, so it's going to be negative 4 plus 2x over x squared, because you could just multiply both top and bottom by x. So, when does our derivative equal 0? Well, that's when negative 4 plus 2x equals 0. 2x equals 4, x equals 2. And when is our derivative undefined, or does not exist? When the bottom is 0, so it's also 0. However, we're told that we want to do this from 1 to 4, to find the extreme values from 1 to 4. So we can just ignore this, because that's not in our range, or our domain that we're looking for. But this definitely is. So then what I do is I'll look at the endpoints and look at the critical point and see what the y values we get. If you define f1, you should get 4 by plugging 1 back into the function. And so we're trying to find, the original, the y values for the original function for each of these points. So like 1, 4 would kind of look like this. F of 4, if you work that out, that's going to be 1 plus natural log of 16, which is 3.773. And f of 2, 2 plus ln 4 will be 3.380, if you work that out. So the graph kind of looks like that. So we see that we have an absolute max right there, and an absolute min right there, and the other endpoint's really nothing. Well, I guess we could call it a local max, but really we're just focused on the extreme values, the highest and lowest. So we would state that we have an absolute min of 3.380 at x equals 2, and an absolute max of 4 at x equals 1. Again, we want like the extreme values. So absolutes. Okay, let's try this one more time. Then I'll sign off here. So again, I'm going to take the derivative of this function. And we have that. So we can rewrite it like this. So let's say f prime x equals 0. Well, that can't be true because our numerator can't equal 0, so forget about it. Where would our derivative be undefined or does not exist? Well, that's when the bottom equals 0, which would be true when x equals 0. So what I'm going to do is I'm going to test my endpoints, and good thing 0 is in that domain. So definitely f negative 1, definitely f of 2, and definitely f of 0. These are the ones I want to test. So if I test f of negative 1 into my original function, negative 1 raised to 2/3 power, you're squaring then cube rooting, or cube rooting the square, however you want to do it, that's 1. That'll be 2 to the 2/3, which would be 1.587. And of course, f of 0 is just going to be 0. So we see that we have an absolute max right here at my right endpoint, and I have an absolute min at my critical point when x equals 0. Oh, some other things I failed to mention, which is pretty important. You want to make sure EVT applies for each of these problems. Sorry, it's Friday afternoon, so I want to get to my weekend. So, and we'll emphasize this when we see you guys early next week before we head out for Thanksgiving. EVT, remember, the extreme value theorem. That's what EVT is, the extreme value theorem. It's got to be continuous on its domain, and it's got to be a closed interval. And we do have a closed interval for both examples 4 and 5. And, these are, you could graph them, but, these are continuous functions. Like, here we have on their domains. 4 over x, is an inverse function, or reciprocal function, whatever you want to call it, rational function. Ln x squared is going to be continuous on its domain. X to 2/3 power functions are continuous on their domains. So we do have to make sure it's closed and continuous, so an absolute maximum can occur. So finally, I'd say my answer is absolute max of 1.587 at x equals 2, absolute min of 0 at x equals 0. Okay, so video's over. So we'll post this to Schoology. Well, of course, you probably know Schoology because that's how you probably got this video. There'll probably be some problems associated with this. And have a great weekend. And finally, go Stanford, beat Cal. I'm saying it's going to be 31-24. And for the football game, we'll say SHP gets 41 in Oak Grove. We'll say 31. I don't know much about high school football, but let's hope we win. Okay, I'm all done.